Folks, we have two more definitions that I want to go through. Those are the definitions of autonomous ODEs, and then we'll look at ODEs with constant coefficients. And we'll talk more about these terms throughout the semester, but I'm trying to get all of these terms out at once. So a first-order ODE is said to be autonomous if it can be written in this form right here. Notice that if it's first order, what I've done is I've isolated the y prime term, the highest order derivative term. I've put this ODE into normal form, but notice that the function on the right-hand side is not f of x, y. Let's just draw attention to that. That's not a function of both x and y, or the independent variable and y. It's just in terms of the dependent variable. Okay? So let's look at this ODE right here. Why is this ODE autonomous? Well, it's first order. Okay, check. It's an ODE. Check. It's autonomous if you can write it in this form. So let's see if we can. So if we go to try to write it in that form, we get 3y prime is equal to 5 plus the sine of y. And as we continue, we get y prime is equal to 5 plus the sine of y divided by 3. And so this is that f of y right here, so it is autonomous. Specifically, this right-hand side, after I put the ODE, the first order ODE into normal form, this right-hand side depends only on the dependent variable y, and it does not depend on the independent variable. Maybe it was x or t in this case. So again, if we go to try to write this in a normal form, which we can do, let's put it in normal form, we get 3y prime is equal to 5x plus the sine of y, or that y prime is equal to 5x plus the sine of y divided by 3. We've put it into normal form, but now it's a function of both the independent variable and the dependent variable, so this is non-autonomous. Okay. So I just want to clarify, the first thing we did was we put it into normal form in each case. Now, again, folks, these are one of these unsatisfying definitions where we say if it can be written in a certain form. I'm actually able to, and you should, after a little bit of work, be able to do so as well. I can look at the original ODE and immediately say that it's going to be an autonomous ODE. I can see that when I put it into normal form that the right-hand side will not depend on the independent variable x because there is no independent variable in that original expression. So sometimes you can immediately look at these ODEs and classify them without any extra rearranging, but sometimes it's unclear, and so you might have to do some rearranging to find out. We could define these we could define autonomy for higher order ODEs, but we're not going to study those specifically, so we won't. Okay. I want to point this out because at this point in the course, a lot of times students are feeling overwhelmed and they're trying to make some sort of hierarchy of definitions for themselves. And I think that's a good skill to try to develop, but it doesn't quite work here with our definitions of ODEs. So we've used two big terms here. We've got the word linear and we've got the word autonomous. And we could have inside linear but non-autonomous, we could have maybe y prime plus xy equals the sine of x. This function right here is linear, but it's not autonomous, so it doesn't fall in the intersection. Likewise, over here, we could have y prime is equal to the sine of y. This ODE is autonomous, but not linear. Then again, there might be equations that are both. So for example, y prime plus 3y equals 5 is an ODE that is both linear and autonomous. Likewise, we can have ODEs that are neither. We could have y prime plus the sine of y is equal to 3x, and we see that this ODE right here is neither linear because of the sine of y term, nor autonomous because of the independent variable x showing up here. So be careful trying to draw hierarchies for these definitions. Stick to the scripts of these definitions. Okay, the last definition we have, it should be pretty straightforward, but I just want to highlight it. We want to introduce this idea of whether or not an nth order linear ODE has constant coefficient functions or not. Remember that we called back when we were looking at our linear ODEs, we called these expressions here, 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 and here, we called those our coefficient functions. And the difference that we have down here is that these are coefficients, but not coefficient functions of the independent variable x. So here, a2 is equal to 3, a1 is equal to -4, and a0 for the dependent variable term, the zeroth derivative, if you will, although that's not quite right to say, the coefficient for y, the coefficient for y prime, the coefficient for y double prime, each of those are constants, so they have constant coefficients, and so the answer is yes. Here, our a2 is equal to 3, that's constant. And likewise, our a0 is equal to 6, that's constant. But our a1, the coefficient function in front of y prime, is a function of the independent variable x. And so this is the reason why we have these are non-constant coefficients. Folks, if you're feeling overwhelmed by these definitions, please don't. We will have all semester to get familiar with them, but it's best to introduce them as early as possible to give you maximum amount of time getting familiar with them. We will now, in the future, study individual ODEs that have some of these properties, maybe some, maybe all, and look at strategies for solving them after we're able to further classify them. I hope this was helpful, and I'll see you next time.